We are on Lesson 7 of Calculus using a textbook by Larson. Chapter 1, Section 4, Continuity and One-Sided Limits. The goals here today are determine continuity at a point and continuity on an open interval. Determine one-sided limits and continuity on a closed interval. Use properties of continuity. Okay, so the easy definition here of what makes something continuous is if you can draw the whole entire graph without picking up your pencil. So you can draw the graph, it's continuous. You can draw the function without picking up the pencil. So the first picture here, when you're drawing it, you got to kind of stop because it's got a hole right here. And then you can keep going. It's not defined at f of c. At f of c, it has a hole. So that's number 1 down here. The function is not defined at x equal to c. This one, as you go from the left, you go up here, then you got to jump down to here. So you had to pick your pencil up. So the limit of f of x does not exist at c because you got a different limit from the left and from the right. And so that's number 2 down here. The limit of f of x does not exist. That's when continuity can be destroyed. And next and last, if the limit of f of x at c does not equal what f of c is. So if f of c, which here is equal to this point, and there we have a hole, so f of c doesn't equal the limit. The limit equals this number way up here, which doesn't equal what f of c was. So continuity is destroyed here by number 3. The limit of f of x exists at x equals c, but is not equal to f of c. If none of these 3 conditions is true, then the function f is continuous at c as indicated. All right. Then on the next page, we're going to look at some pictures and talk about continuity. So it says use the graph to determine each limit and discuss the continuity of the function. All right, so A, we need to figure out the limit as x approaches c, and on this one, c is -2. So as it approaches the number -2 from the right, then we got to look at the limit as x approaches -2 from the left, and then we got to do the limit as x approaches -2, all of f of x. All right, so from the right, so going into -2 from the right, it's coming close to the number -2. And coming in from the left, it also is coming to -2. So that makes the limit as it comes to -2, -2. And if you do f of -2, it's also equal to -2. Therefore, the graph is continuous. Therefore, f of x is continuous. At, let's see. Well, we'll just say it's continuous. All right, next one. They want us to find the limit again as x approaches, let's see, -3, because c on this one's -3 from the right. And the limit as x approaches -3 from the left. And then what's the limit as x approaches -3? So as it approaches it from the right, it's coming close to number 3. From the left, it's also coming close to number 3. So the limit's 3. And then if you do f of -3, if you look at the picture, because there was a hole here, it's equal to the number 4. So because that's true, the graph's discontinuous at that point. So f of c is not continuous. Therefore, f of x is not continuous. So same question here on number 10. So the C value this time is -1. You can see just looking at it, it's not continuous, but we're supposed to say why it is mathematically using that definition. So the limit, this is letter A, as x approaches -c from the right. Then we want to do on B the limit as x approaches -1 from the left. So then what is the limit? And then last of all, we want to find f of -1. All right, so -1 from the right, you get 0. And then -1 from the left comes close to the number 2. And then so the limit does not exist. And then f of -1 is actually 0. So it doesn't exist for a lot of reasons. The main one being that the limit doesn't exist at that point. So f of x is not continuous. All right, and so the actual definition here is of continuity on a closed interval. If a function f is continuous on a closed interval AB, when f is continuous on the open interval AB, and f of x is equal to f of a when you're taking the limit of it, and f of x at another point B is also equal to f of b. The function f is continuous from the right at A and continuous from the left at B. All right, so that's a continuous interval. So even though it's doesn't keep going over there, it's continuous on that interval because it has a limit from the left. Well, it has a limit here going this way, and it has a limit going that way to the, well, let's see, that'd be going to the right, and this way going to the left. It's got a point that it's coming close to. All right, so in 36, they want us to discuss the continuity of the function on that closed interval. Okay, so what we should do to discuss in here is we need to look at the limit as x approaches the left, the -3 from the right, and then we want to look at the limit as x approaches 3 from the left of f of x. All right, so it'd probably be best if we looked at the picture of it on the calculator. That would be the quickest way to do it. So looking at it on the calculator here, let's see here, y equals, and I was doing a trig function, so I'm going to have to make sure I clean up the zoom. So it's 3 minus the square root of 9 minus x squared. 3 minus the square root of 9 minus x squared. And so, yeah. All right, let's graph it. Well, I better fix my zoom, standard. All right, so looking at that, at the table here, so it stops at 3, 3, and it comes in at -3, 3. And it goes through 0, it looks like. Let's double check it. Yes, 0, 0. All right. So that is continuous. There's no holes on it. It's continuous on that interval, so showing it mathematically, as we get to the -3 from the right, it approaches the number 3. And then -3 from the left, it approaches the number 3. And then if we did, yeah, that shows it. So, and then if we did f of -3, we also get 3. And if we do f of +3, we also get 3. So the limit as x approaches -3, those are both equal. And as it approaches 3, those are both equal. So by the definition of what makes it an interval, the closed interval, continuous, it's continuous because everything's there. Okay, let's look at the next one. Okay, so we got 1 divided by x squared minus 4. So remember to use parentheses around that. So y equals 1 divided by parentheses x squared minus 4. So it's got two vertical asymptotes because the denominator factors in the x plus 2 times x minus 2. So you got the vertical asymptote at positive 2 and negative 2. And as it goes to infinity, is y goes to infinity, well, as x goes to infinity, again, what you do is you look at the highest power x on the top, which there isn't one, so it's 1. And the bottom is x squared. So as the graph goes to infinity, it goes to 0. So it has, to the left and the right, the graph is approaching 0. So y equals 0. All right, so now on the calculator, it looked like this. Just a brief, quick sketch of it. All right, so looking at that interval then. So if we do the limit as it goes to negative 1, of g of x, and when we go to negative 1, we want to go to it from the right. So as we go to the number 1 from the right, it does approach a number down there. Let's see what it is. So second table, negative 1, it's negative 1/3. And then if you do g of negative 1, which we just did, it's negative 1/3. And then if you go to the number 2, so the limit as x approaches 2, and we're going to want to approach it from the right. No, from the left of g of x. So as we come to the number 2 from the left, it's not going to exist because it's going without bounds down to negative infinity, so it's not approaching any specific number at all. So it doesn't really exist. So therefore, the graph is discontinuous. So therefore, g of x is discontinuous. And you could say at that point 2. So it's that interval. They were asking about the closed interval. The closed interval is not continuous. All right, on the next page, it says removable and non-removable discontinuities. Find the values of x, if any, for which f is not continuous. Which of the discontinuities are removable? All right, so on this one, you've got a vertical asymptote at 6. It's x minus 6. So 1, 2, 3, 4, 5, 6. So x equals 6. And then you got 4 over x, so it's going to have a horizontal asymptote of y equals 0. And if you put in your calculator and graphed it, you would have seen that it looks like this. So they wanted to know, does it have any removable discontinuities? Well, you're going to have that big gap right here. It jumps. And so it's got a domain error there at the number 6, so it's not continuous at 6, and we can't remove it at all. So it has a non-removable discontinuity. At x equals 6. All right, on the next one. So I kind of overachieved graphing it for you, but I know you're still working on how to graph things. Okay, so this one here, it doesn't have any vertical asymptotes because there's no way to make the denominator equal to 0 on it. And if you graph that on the calculator, it's kind of fun to look at. We'll look at it. So we got y equals 1 divided by x squared plus 1. Ooh, I forgot parentheses. There we go. Okay, so you can see it goes up at 0 to the number 1, and then it goes down forever to the left and right, but it is continuous. There's no holes or anything. It just keeps going. So it's continuous on the whole thing because there's no holes and no gaps, and there's nothing there. So it's continuous. So it wanted us to find the x values of any of which f is not continuous. There weren't any. Which of the discontinuities are removable? Well, there weren't any discontinuities, so none of them are removable. So really all we have to write is that it's continuous. Drawing the picture always is fun too. All right, this one is, since we can factor down here, that's x plus 2, so it's going to have to be x plus 2. They always play that game. So then that's x minus 3. So it has a removable discontinuity at x equals negative 2. Removable discontinuity at x equals 2. It's got a hole there at x equals 2. And then looking at it though, we still have a vertical asymptote though at 3. And as we go the highest power on the top over the denominator, x over x squared makes 1 over x. So as you go to infinity, that's becoming 0. So you got y equals 0. And if you put in your calculator to look at it, it looks like this. So you also have, besides for that hole that we have that we could remove, we still have that problem there at the number x equals 3 because of the vertical asymptote, and that's not removable. So non-removable discontinuity at x equals 3. Therefore, f of x is not continuous. I think that's all we really have to do on it. Okay, I'll see you for the next lesson.